Reassessment video for potential energy. The question that I created goes something like this. In an adventure movie, a 62.5 kilogram stunt woman falls 8.10 meters and lands on a huge airbag. Her speed just before she hit the airbag was 10.5 meters per second. A. What is the total work done on the stunt woman? B. How much work is done by gravity on the stunt woman? And then I'll come back and read this one after, because I changed up the scenario and it's a different idea. So, A, the total work done on the stunt woman is found by calculating the increase in kinetic energy. And since this is the picture I drew, since the stunt woman's acceleration is constant, we can use this equation. Work equals 1/2 mass times velocity squared. We know the stunt woman's velocity is 10.5 meters per second, and we know her mass is 62.5 kilograms. So we're going to plug this in, and it comes out to approximately 3,445 joules. It's joules because kilograms times meter squared over second squared is joule. And like I said, so it's the total work done, and it's also the increase in the kinetic energy that we're finding in this equation here. So now in part B, we have work done by gravity on the stunt woman. And in this, we're going to use this equation because what we're going to find here is actually the decrease in the gravitational potential energy of the woman. And we're going to use this equation that the work done by gravity equals mass times gravity times h. H is going to be our distance, 8.1 meters, the distance she falls. And we know all three of those values. So gravity we know is 9.8 meters per second. We know this, and we're going to plug them in and get approximately 4,961 joules. Then part C says that rather than an airbag, the stunt woman encounters a springboard. And the springboard has a spring constant of 3,500 newtons per meter. Also, the woman is not falling straight down now. She is falling at an angle of 30 degrees onto the springboard. And the question says, what is the greatest distance that the springboard will compress after she lands on it? And we're going to assume that there's no energy that's lost from air resistance or friction. So this is my new picture. I didn't spend much time on my drawings for this video, but alright, so now the only thing that has changed is that she's falling at an angle and she's falling onto a spring. So the maximum compression of the spring is going to be the stunt woman. The system is the stunt woman plus the earth plus the spring. These are the three things at play here. So we want to use this equation. W equals the change in kinetic energy plus the change in potential gravitational energy plus the change in potential spring energy. Now in part A and B we found this and this, but it was for when she was falling straight down. So let's do it again. The change in kinetic energy is going to be the final kinetic energy minus the initial, and we know that our kinetic energy is found by 1/2 mv squared, mass times velocity squared. And at the final position, the lady has no velocity. She's stopped. She's on the ground. So this is going to be 0. The final is 0. The initial, however, she does have a velocity and a mass, so we're going to calculate this. So this is the same as part A, but I kept a few extra decimal points to help us out later. The gravitational energy, we're going to redo this one. The mass times the gravity times h. But now h is different, isn't it? Because she's falling at an angle. Our h is 8.1 meters times cosine 30 degrees times cosine the angle. And we'll use cosine because we're looking for the hypotenuse, and so that's gonna help us to solve that. So we'll find that h equals approximately 7.0148 meters. So we're going to use that in our equation over here, and we're going to find that at the final position, she has no height. The height's 0, so it's going to be canceled out. So it's going to be 0 here. That's at the final, but at the initial position, she does have a mass and gravity and a distance that she's falling. So we're going to get approximately negative 4,296 joules. So now we have this, and oh, I didn't explain this. The spring potential energy is going to be 1/2 k s squared, and the k is the spring constant, which we know to be 3,500 newtons per meter, and the s here is going to be our distance that the spring compresses. How much will it? Initially, the spring is not compressed at all. It is at rest, so this equation goes away. Initially, it's 0. Finally, it's going to have a compression distance, so we're going to use 1/2 3,500 newtons per meter times s squared. We're going to put all three of these values into our equation for work. Work equals the potential kinetic energy, the change in kinetic energy, plus the change in potential gravitational energy, plus the change in potential spring energy. We're going to use algebra to solve this. Solve for the s, take the square root here, and we'll get approximately 2.10 meters. And we can always take this value if we want to see if we did it right and put it back into this equation. W equals this plus this plus this, and upon doing so, I discovered that we were right, and that it's approximately only 0.102 meters off, and that is due to rounding, differences in rounding.